Today we're going to be looking at the equations of motion. We're going to study the motion in one dimension, an object that is speeding up or slowing down. We'll learn the three equations of motion, the three main ones. There are more, but the three important ones to help you find anything. And we'll do some practice problems on this. So first things first, you have uniform motion, as you already know. You have a speed time graph going straight in a straight line, constant speed. If you wanted to calculate the distance, you could just do distance equals speed times time. We already know this. This is the area under the graph as well, funnily enough. Speed times time. So that's for uniform motion. But now we're going to look at the other type of motion, accelerated motion. You could say uniform acceleration or changing velocity. You will have a slope. We already know how to find the acceleration, Vf minus Vi over t. That is actually going to be our first formula. But then if you wanted to find the area under the slope, you realize that there are two shapes and so on. There are formulas that will help us solve any question when it comes to acceleration. These are the three main ones. The first one, like I said, is A equals Vf minus Vi over t. We've rearranged it to write it like this. Vf equals Vi plus At. The second one is x equals VIT plus a half AT squared. Just to remind you, x is the displacement. Sometimes it's y. If it's going up and down the way, we can say y. But if it's horizontally, we will say x because it's the x-axis. Initial speed, final speed, acceleration, and t is the time. The third formula, if I did not have time, I can use this. So the whole point here is that if I have the simple formula without a distance, I can use this rule over here. However, if I did not have the final speed, I do not know it, or I don't know something else, I can use this formula here because I have a distance and there is no final speed. And like I already mentioned, if I do not have time, I can use this rule here. Alright, here are all the formulas that you could use. A little cheat sheet, pretty much the same ones that we've just talked about. If it's acceleration being negative, we could just replace this with minus, or you can write minus in the A. You will get the same answer. We've mentioned this one. To find the average velocity, which is what we have kind of done in the lab, is you add the two speeds together and divide by 2. Final plus initial divided by 2. So this is not as important, but you know how to do this. Finally, another one that can be used is this one here. If you want to find the displacement but you know the final and initial speed, we can do a half Vf plus Vi over t. We could also use this one. But again, no need. The more important ones we have is the first one, the second one, and this one over here. The ones I've shown you before. These three, you can find everything you need. Here is a little toolbox for you. Every time you have a question that comes up in equations of motion with a bunch of numbers and letters, you use this. X, Vi, Vf, At. Put the numbers in. And then you choose the best formula based on the numbers that you have and what you are looking for. Here is an example. A space rocket's traveling at 20. It accelerates at 5 for 2. How far does he go during the 2? So, we want to know x. We have Vi, we don't know Vf. We have A, and we have t. So what I would normally do is write it on the side, but there's not much space here, so I'll leave it like this. X is what I need. So obviously this formula is no good. I have the second and the third. I do not have Vf, so the third formula is no good. Maybe I can use this one. Vi, yes I have. T, yes I have. A, yes I have. We can use this rule. We can substitute the numbers into the rule now. 20 times 2 plus a half times 5 times 2. Okay, 20 times 2, which is the time, and then a half times 5, because that's acceleration, times 2 squared. 40 plus 10, it gives you 50 meters as the final answer. Here's another example. A train is traveling at this speed, decelerates to this speed at this acceleration. How far does he travel while he is decelerating? Again, how far? Distance. Straight away, I know that this rule is no good because there is no distance in this formula, so I will not use it. I have to find x, I have Vi, I have Vf, I have A minus 2 because it's decelerating, so actually it's minus 2. and we need to find x. We don't have t either. So what rule? I do not have t. I cannot use this rule. So that means I have to use this rule and I have to change it to get x. I have to rearrange. There is a way in your calculator that you can use shift solve and get the answer, but if you don't know how to, we will just rearrange the formula. So we'll use this. Rearranging, I'll take the VI to the other side, it becomes minus, and then I'm going to divide by 2a on both sides, so it'll be divided by 2a. So I will do 15 squared minus 45 squared over 2 times negative 2. The final answer will be a displacement of 450 meters. A third example here for you. A train is traveling at 7, accelerates at a rate of 1 for a distance of this. What is the velocity at the end? Again, writing down the information that we have. Starting speed is 7, acceleration is 1, displacement is 25.5, VF I need to find. Do I have a time in here? There is no time. So straight away, now that I know there is no time, this is gone and this is gone. I will have to use the last formula over here. Vf squared equals Vi squared plus 2ax. The final velocity, well that's easy, that's what we need, no need to rearrange. 7 squared plus 2 times 1 times 25.5, and you will get your answer of 100 meters per second squared. No, actually that's not finished yet, because that's actually squared. Almost got stuck there. This is Vf squared, not good. We need to be Vf. So we have to finally take the square root at the end of 100. That's 10 meters per second squared. So don't fall for this trick, okay? This is not the final answer. This is Vf squared. We don't want that. We want V. So we do the square root of 100. Very good.